And she's probably gonna live on campus next year. Are you on campus?
Yeah.
And can you have track scholarship, right?
Yeah.
Yeah, that's what I
Alright,
think
in
she
case
needs
you
to do.
guys did not get the online homework, I got a copy here.
It wasn't there.
It wasn't there yesterday, day before yesterday when I said it would be, but it was there yesterday.
Whatever.
I need it.
It wasn't there yesterday for the most day.
Well, yes.
Okay, thank
But it was
you.
I
there
would have
yesterday.
started it anyways.
And it was a good thing.
I don't really have to start it either way.
Anyway, I'm sorry.
And we are the lazy ones.
Huh?
And I said, and we are the lazy ones. Because he called us lazy.
I wouldn't have started this anyways. I'm probably
Yeah.
not gonna start it until Monday.
Tuesday probably because I have a test on Tuesday. More about.
No, the 100 watts would be. I mean, just assume that power per time is quantities. Don't worry about it.
So, is this over sound? Is this over like, what is this section over, like sound or?
The first two problems are intensity, which we're over. After that, it's fluid.
Oh yeah,
What's the city in?
fluid.
I think he's clear.
All right. So last time we were talking about we started talking about fluid, then we talked about pressure and density, right? Let's do a few more examples of pressure. Say we have a car with some flexible wheels, 4 flexible wheels, 4 flexible tires, okay? The inside tire is inflated to a pressure of, let's say, 30 psi. 30 psi. You know, psi is a pound per square inch. It's the English unit for pressure. Now, this isn't good units for us. 1 psi is actually equal to 6,895 pascals, which a pascal was a Newton per meter squared. My question is, suppose this car has a mass, or suppose it's a car that has a mass of maybe 2,500, like in front, kilograms. Okay. What is the area of the tire that's on the ground? The area of the tires that are on the ground. So that's my question. And I'll go ahead and we'll do this one together. So what would be a good approach to this, do you think? So first of all, supposing the tires are nice and flexible, the tire pressure on here is 30 psi. This pressure won't be changing in the tires with the weight on there. It's inflated to that with the weight on there. That means every square inch of tire here has 30 psi pushing downwards on it. And it's balanced, it's not inflating, that means 30 psi could be pushing upwards on the ground from that. So, what does that mean? It means that that if I had like a square foot with 144 square inches of tire laying on the ground, then I just multiply that by 30, that's how many pounds that square foot's supporting. Does that make sense? All right, so let's go ahead and see if we can do this. So, does that make sense? All right. What's that?
625 kilograms on one tire.
Okay, that's right, that's right. So if we have 4 tires, but we're interested in the total amount of all the tires. What is the area of the tires on the ground? All 4 together. So what's the force? Let's draw a free body diagram for this, okay? Let's draw a little free body diagram. I have a gravity force going downwards, right? Normal force going upwards. Sum of the forces is what?
Equals 0.
Yeah, so the normal magnitude of the normal force is equal to mg. If I look at the detail of the normal force, that's the force that's being supported by the pressure in the tires. So this normal force would be the pressure times the area on the ground of the tires. Does that make sense? You look like you're...
Yeah, I'm confused. I don't know.
All right, so say I have this tire 30 psi. Say on the ground that you have a square inch of tire on the ground. How much pressure is that tire pushing down on the ground with?
Like,
Or what's the force on the ground if I had like 1 square inch?
by 1. If you have 1 square inch?
Say I have 1. What does this mean? This means that every bit of the wall of the tire, every square inch of that has 30 pounds of pressure, or 30 pounds of force on it.
Oh, so that's by 30 pounds it would be pushing on 1
Yeah,
square.
so if I had 1 inch on the ground, that's being pushed down on the ground, that would be 30 pounds on there. Okay.
Against the ground, you're gonna have 30 pounds of air pressure on that square inch. Plus, you're also gonna have your weight of the whole thing.
Well, the tire inside here is 30 psi, it doesn't change.
That's the same when your normal force is in the carrying. You've got your weight pushing down.
Yeah.
You've got 30 psi on top of that.
No, the 30 psi on the part on the ground
So,
is supporting that weight.
so he's saying the area of the tire will increase or decrease so that the pressure is 30 psi.
That's what I'm right. The tire will warp, and so more and more areas on the ground until you have enough area so that the pressure in the tire can support the vehicle. It's the pressure that's supporting the vehicle. That's where the normal force is coming from. Although with run flat tires, some of the stiff walled tires, there's a fair amount of force from the wall too. But that's why I'm using flexible tires here. Like drag racing tires, for instance, or big tractor tires.
So basically mg is equal to PA because the pressure in the tire is what's pushing the car upward, which is the normal force.
That's right. Does that make sense? A little bit tricky to get your head around, but when you start to look at it, you can start to think about it. Like, you'll see like semi trucks on the road, and you're like, oh, why do they need 18 wheels? and then you start to look at just take a look next time and kind of estimate how much of the area of that tire is actually resting against the ground. And if you know that they're about 60 psi for those tires, you can start to estimate roughly how much they're carrying. So anyway, let's go ahead and see if we can do this, okay? So this is mg. PA is, okay. We know what everything is but area here, don't we?
Mhm.
Okay, so that means that area is mg over the pressure. That'd be 20, what's that?
Do we do the pressure of all 4 tires, so it'd be like 120, or not?
No, just the pressure in any given tire. And then this would be the total area of all
One
4
tire.
tires on the ground.
Why wouldn't it just be of 1 tire if we're only doing
Because
one?
if I put the M for the total mass of the car,
It's all 4.
yeah, whether I had it supported on 4 or 8 tires or whatever, it doesn't really matter. In this case, I'm just looking at the total area for the given 30 PSI that's supporting that weight.
But it's more than 30 PSI, isn't it 30 times 4? If there's 4 tires.
No, each tire has 30 PSI. By adding more tires, all I'm doing is I'm increasing the area on the ground, or decreasing the amount every given tire has to squeeze down to have the right area on the ground.
Okay.
Does that make sense?
They're gonna put their shape better. That will be the same area.
Because if you add another tire, the areas for each tire is going to decrease, so the
Yeah.
total area would be the same anyways.
Yeah, that's right. All right, so what would be this area?
Yeah, that's what I got, 0.118.
Okay, so 6, 8, okay, so we want mg, which is 2,500 kilograms times
9.8.
9.8 meters per second squared, divided by 30 times 6,895 meters squared. All right, this is a Newton, this is Newton per meter squared, units area, good. All right, when I do that, you get what?
0.118.
0.18?
118.
118 meters squared. Okay? So what would that be? That's, each meter has about 9 square feet, maybe more like 10 square feet per meter. So you're looking at maybe a square foot of tire on actually resting on the ground, which is fairly reasonable. So if you look at tires, when they're on the ground, they don't meet at some point. They meet kind of like this, flatten out a little bit, like that. This width here, multiply that length by the width of the tire, and that's your area of each of the tire on the ground. And you'll see that, if you start to pay attention, that type of thing will make sense. The question that I want to ask is, why would you use gigantic, have you seen these gigantic dump trucks that they have on mines? These are some of the biggest vehicles in the world. They have, they carry, they used to be 250 tons of payload. Now they have like 300-ton ones, even bigger. And but they use, these 12-foot tires or something. So why would you use such a gigantically large tire, but not that many of them, to support that amount of pressure? Well, the issue is actually rolling resistance. Like if I have a really big tire, it doesn't take much of squishing before you get a pretty big area on the ground. But if I have a smaller tire, I'd have to squish it a lot more to get a big area on the ground. So it actually makes more sense to have really large diameter tires to support big weights. Just because the tire doesn't have to deform that much from a circle to have a fairly big area on the ground. So you don't, make sense?
Also doesn't beat your roads up as bad.
What's that?
It also doesn't beat your roads up as bad.
That's, yeah, because you really want low ground pressure. And they don't do it to 30 PSI there, I don't think. I think it's less.
No, they're really low pressure.
Less than
The
that.
ones on the tractors, does anyone know what the big tractors, what their PSI, what their ground pressure
Depends on
is?
the tires.
What's that?
It depends on the tires.
On my car it's like 45.
Some of the small, like your front wheel assist tires, they're pretty high pressure.
Yeah, but what about the big one on the back?
I don't know, I haven't messed with the really big ones.
Anyone done that? I'm curious. What? Like for
Measure
a
the
tractor.
PSI of a tractor
I'll
tire.
measure this one. I feel like a tractor tire has really thick walls though. And
Yeah,
the
yeah,
tread
there's
is
something.
also like,
There's some.
Huge. Yeah.
All right. Okay, so maybe you guys can start thinking about that and what you think it's kind of fun to think about.
This is stationary, correct?
What's that?
This is stationary.
It's stationary, but it shouldn't really matter much.
The area does change somewhat with motion.
Well,
Tire deformed.
Well, on a drag racer, yes. Because the drag racers, they go from wide tires to very narrow tires when they spin it up crazy. I think in normal tires, that doesn't really change much.
15's a good number.
What's that?
15's a good.
15 PSI, so they use a lot lower than road pressure because it's keeping less, it puts less pressure on the dirt.
15.
Yeah. They have, by the way, they have, the tracks. You know, a lot of things now are, particularly with the no-till, right, they use tracks. And that's so that they can have lower ground pressure. Because they have the tracks, you know, all that area is on the ground. And so you can have lower ground pressure to support the same massive tractor, and so you damage the dirt less, I guess. I can, really? That's pretty neat. All right, let's go through some more pressure stuff. Okay, here's a rule. This is for incompressible liquids. This is the basis of hydraulics, actually. If you change the pressure in one part of the liquid, the pressure throughout the liquid changes by the same amount. In one part of a liquid, changes by the same amount. So, if I have a liquid that's confined to a tube or something like this, so this is all full of the liquid. If I increase this pressure by, say, P by 1 Pascal or something like that, the pressure over here will increase by 1 Pascal. That makes sense? So this is just a rule. This is experimentally verified. By changing pressure over here, it changes by the same amount over here. So anything I put in here will experience a different force per area. If I change the pressure way over here. And this turns out to be the basis for hydraulics. So let's say that I have a pipe that narrows down to a different area. And let's say that I have like some sort of piston in here. And and a little piston in here. And then there's fluid in between these pistons. Okay? It's called the area of this pipe A1, and the area of this end A2. These pistons are free to move back and forth, okay? But, you know, at this point where there's no forces on them or something, they're just stationary. Let's say that I take the piston on this side and I exert a force F1 here. So I press in this smaller area with a force inwards direct of F1. Magnitude of force is F1. I'm leaving off the vector. I'll put it up there. What would happen over here if I did that? Well, if I press this inwards with a force F1, the pressure changed by an amount, the change in pressure is equal to this force times the area of this piston, right? Force times area? Made a mistake, right?
No, it's
Force per area, right?
yeah, it's
So force 1 divided by area 1. That'd be the change of pressure if I pushed inwards on this side piston. Well, let's see what the result of that is over here. So I have a delta P over here of F1 over A1. So that change in pressure would end up exerting a force on this piston, wouldn't it?
A1 or A2? A1.
So the change of pressure everywhere
Oh, okay.
is F1 over A1. I change the pressure by F1 over A1 here, that means the pressure everywhere in here changed by F1 over A1. So this change in pressure exerts a force that way on that bigger piston, doesn't it? The total force, F2, would be the change in pressure over A1, or the change in pressure, not over A1. The total force would be the change in pressure times the area of the second piston, wouldn't it? So if I was looking at the force on the second piston, I just look at the pressure on it times the area. So change pressure times A2. So I take this change in pressure here, substitute it in, and I get that F2 is equal to F1 A1 A2. And I could rewrite that as, maybe simply make it a little bit clearer. F1 A2 over A1. So if I have a tenth of the area here as here, and I exert like 1,000 Newton force here, I get a 10,000 Newton force over here. Does that make sense? So let's do, and this is the principle behind hydraulic lifts, hydraulic stuff, like pressurizing fluid. I can really change forces over large pistons by quite a lot. So let's go ahead and see this. I'll draw. Let's do hydraulic jack, okay? So hydraulic jack. We won't worry too much about the details of it. But let's say that there's a piston here that's supported by hydraulic fluid through it. let's say that this is actually has a cross-sectional area that's a circle. This piston is a cylinder, let's say it looks like a circle, you know, if you look at it from above. Say the radius is 3 centimeters. And let's say over here, there's a little, the tube narrows a bit, and I have the little piston that may be being pressed in by a screw or something like that. And the force that it exerts here is 2,000 newtons. And that's not too rough to get. That's about the weight of a 200 kilogram mass. If you screw something in, that's not too bad to get. But this is 0.5 centimeters in radius and then it. So if this end of a hydraulic, if I'm changing if I'm exerting a 2,000 Newton force here over an area given by a circle with a radius of 25 centimeters, how much force is being exerted up here? Question mark. So go ahead and work with the person next to you. Give that a try, okay?
Do we have to change it?
What's that? Well, luckily, if you get the areas, they
You
notice
can
how.
do it in centimeters squared, or
Notice
centimeters.
how their ratios, because whatever units you use for area, as long as we're consistent,
Okay.
those units will cancel out.
That one.
But keep in mind that what I wrote is a radius,
Yeah, so
so you have
So
to
area
convert that
squared.
to, you have to figure out the area.
2 pi r
What's the area of a circle?
2 pi r
Squared.
squared.
Well, 2 pi r squared, is that the area of the circle?
Isn't it just pi r squared?
Pi r squared.
Pi r squared?
Oh, I'm like a pi.
Why did we say 2 pi r? Wait, isn't it 2 pi r?
2 pi r is this. Is the circumference 2 pi r?
2 pi
Oh,
r
2 pi r is the circle.
Pi r
Pi r
squared
squared is
is the area.
Oh gosh. Do we need to change the thing or something? Yeah, I'd like to change another ratio.
So these jacks are actually pretty potent.
I just did F2 equals F1. A2 divided by A1.
Okay, you ready to go through it? What did you get?
A lot.
What did you get?
719, no, sorry.
7,104,000.
Yes. No, 71.
72,000.
Basically 72,000.
I got 4,005.
Wow.
He got 720.
All right, let's go ahead and see what's going on, okay? I think the 72,000 might be
Yeah,
right.
You got same
He
as
got
me, too.
72,000.
That's what I got.
Okay. Which, by the way, is about the weight of, about a 7-ton mass. So it's this would be like a 7-ton jack. Okay, let's go ahead and see this. So we have. I'm going to call this F1, and then F2 here. So I have my formula that F2 is equal to this magnitude of F2. The F1 times A1, A2 over A1, right? This up here would be A2. This here would be A1. A1's where F1's exerted.
Yeah.
All right, those are circles. This would be pi r2 squared also pi r1 squared. These pi's cancel out. Notice the units, whatever units I measured these in, are going to cancel out too. Okay, so this would be F1 times the ratio R2 over R1 squared. Write it that way. This radius is 6 times that radius. So this would be F1 times 6 squared, which is 36 F1, which is 72. Makes sense? All right. So that's hydraulics, and you can see that a lot of times here, you don't just exert a force here. You just put in you just pressurize a fluid. Using compressed gas, using various other ways. Pumps. Yeah. However way you want to do it, you just pressurize a fluid here, and then that change of pressure would exert a force on the piston at the other end. And you can get some very large forces out because it's fairly easy to pressurize a fluid to say thousands of psi. All right. So let's go ahead and examine pressure at the bottom of lakes and oceans. Pressure as a function of depth. And this will also lead us to understand the buoyancy force. Okay? Let's say that I have a lake and the water, let me get room for water. Okay. The water in this lake has it's filled with water, a basin. All right, let's suppose that I have a box in this lake, and the top of the box has an area A. If I look above this box, there's a column of fluid. That has this column of fluid there above the box. All of this fluid because there's no shear force, resistance to shear force, this fluid is all being supported by whatever's down here. Okay? Do you see that? That if I put something in here, the weight of this fluid is being supported by that box right there. Now, let's say that this is a depth D, and that there's a density rho of fluid. All right, now let's say that I have a density here, depth D here. The area of this box is A at the top. What's the mass of fluid above that box?
Density times your,
Yeah, density volume.
Yeah, that's right. So mass of fluid, M, fluid, would be the density times the volume of this column of fluid, right?
Mm-hmm.
The volume of that would be just the area times the depth.
Mm-hmm.
Rho area D. Okay?
Wait, what?
Where's the density?
Density.
The density of the fluid.
Okay,
Oh, yeah.
So density times volume is a mass.
okay.
So density is mass per volume.
Density.
Length times depth or area times depth?
Well, length times depth, is that a volume?
No. Volume is 3 units. Whatever.
Yeah.
Yeah,
So
area.
it'd be area
Times.
times depth would
That
be the
makes
volume of a column. So think of it as a cylinder. The volume of a cylinder is pi r squared times the length of the cylinder. So area times,
So the area times the length.
yeah.
So,
And for anything that's tube-like or anything like that, it's always the same. Area times length. All right, so this is the volume. This is the mass of fluid here. How much would that weigh?
Did you tell us the thing? Or how much the depth?
Just be the mass times
Yes.
gravitational.
Oh.
No, that's a force.
Only the letters.
So this is the mass of the fluid. That means that if I look at here, there has to be a normal force on here, whatever mg is for this fluid. If I were to draw a free body diagram for that fluid, I have normal force upwards, mg downwards. Those have to balance if it's at rest. And so the normal force on this box would be mg. So that means the force going downwards here, F is equal to mass of fluid, rho, A, D, times G.
so, okay.
So this force, the force would be
So the force of the box.
rho, yeah, the force on the area of the box would be rho, A, D, G. Now, this is the force. What's the pressure on the box? Take a little piece of the area of the box. What's the pressure be? So let's look at this depth of fluid here.
Pressure equals force over area.
That's right. So pressure is force per area, right? So the pressure that the fluid exerts on this box here would be rho GD, right? Be rho A dB divided by A is rho D. So that actually turns out to be the formula that we need. At a depth D inside of a fluid, this is of course on Earth where acceleration due to gravity is G. If it was on the moon, you take whatever that.
Well, is G the same in the water?
Yep. Gravity acts on all masses at the surface of the Earth, so if it's pretty close to the surface of the Earth, you're good. So I would have the pressure is rho dV, density of fluid, depth below the surface. So just to calculate, make sure that we understand how to use that. Oh, by the way, also, there's one other thing. If you want the total pressure here, if there's atmospheric pressure also on here, I have to add the atmospheric pressure up here, because that thing is also pressing down. So in general, I also would put a P atmosphere here as well. By the way, atmospheric pressure, it's about 14 PSI.
Is that 1 ATM?
Yeah, that's 1 ATM. P atmosphere in SI units, 101 kilopascals, or 1.01 times 10 to the fifth pascals. Okay, just so you know. Pascal's a pretty low unit of pressure. All right, let's just calculate it really quickly. Let's say that you're 1 kilometer deep in the ocean. How many atmospheres of pressure would a submarine down there experience? So let's say I have the ocean, submarine, now I'm using yellow. Submarine little box, depth 1,000 meters, density of ocean water, density of fresh water is 1,000 kilograms per meter cubed, right? Density of ocean water is a little bit more, because it's salt water, 1,025 roughly kilograms per meters cubed. And for an incompressible fluid, it doesn't change much as you go down. So go ahead and see if you can figure out what the pressure is at 1,000 meters depth.
Where's the pressure?
Do you have it?
Yeah, that's what I got.
What did you get?
Yeah, 10 basically rounded up.
10 to the 7.
1.01, 1, 2, 3, 4, 5, 6, 7. Yep, 10 to the 7.
Let's go check this really carefully. Okay. So we'll just plug it into this volume. So or this formula. So pressure at 1,000 meters would be rho 1025 kilograms per meter cubed times G 9.8 second squared times D 1,000 meters plus P atmosphere. Times 20 pascals. So this times this times that turns out to be about 1,000, or
Yeah.
about what, 10 million
Uh-huh.
plus 1. I think that's about right.
So
So the
the pressure what?
So this, kilograms, meters, so you should have kilograms, meters squared per second squared. So the kilograms meters per second squared, that's Newton. Okay, so we want a Newton per area.
Is the pressure
Yeah.
above the box in pascals?
And that would be, and it's about 100 atmospheres, right?
Wait, so our unit is PA? Or?
Yeah.
So then so the total pressure on the thing is gonna be that huge number plus 1 atmosphere. So really, the pressure of the water is way more.
About 100 atmospheres.
Isn't it every 33 feet, like, goes up by 1 atmosphere?
Yeah, and you get that to about every 10 meters. So that means if you're on the bottom of the deepest part of the ocean, you're looking at, which is like 11,000 meters, you're looking at about, 1,000 atmospheres roughly.
Does gravity change any as you get, say you're at the bottom of the Marianas Trench? Is gravity any different there than it would be at sea level?
Slightly, but it's not really noticeable because you're down only, the Earth about 6,000 kilometers in radius, and if you're down 10 kilometers, you really haven't changed the radius that much.
So if you asked us to find how many atmospheres of pressure is on that, would we do that number plus 1 atmosphere divided by 1 atmosphere?
No.
No, just that number plus 1 atmosphere, yes. Oh, how many
Like,
atmospheres? If I asked for how
of
many
pressure it
atmospheres.
is.
Yeah.
But you have to add the 1 atmosphere
Yeah,
too,
that's
right?
right. Okay. One more thing. We got 3 minutes. And, we'll do some examples of this. Okay, let's go back to this box here. I'm gonna read these up. It's called height of this box H, okay? Area of this box H. The pressure, the depth of this top surface is D, the depth of the bottom surface would be D plus H, wouldn't it? So up at the top surface I have a pressure P1, at the bottom surface I have a pressure P2, pushing inwards. P1 is equal to rho G times D. P2 is rho G D plus H, because I'm a further distance H down. The difference in these pressures, if I look at the force on each side of this box and on the top surface and the bottom surface, my force on the force on the bottom surface would be pushing it upwards, the force on the top surface by the pressure would be pushing it downwards. So if I looked at this F2 minus F1, this would be the net force pushing it upwards due to the pressure. And this would be rho G D plus H A minus rho G D times A.
Because force equals pressure.
Yeah, because force is pressure times area.